Okay, so hello. Now we will be talking about third automata, and this today's concept will have applications in two of our research groups. The first research group will be the information theory group, which is responsible for the implementation and the genome sequencing group, that is responsible for the practical application. So application, or no, not the implementation, more like the implementation. How do I say it? Let's just call it implementation. It's not that important. Implementation and the application. Okay, so basically the information theory guys are going to make our automata and we're going to use it in genome sequencing. So first we're going to start with talking about what a third automata is. So we are assuming that you know that assuming an automata is clear. So I'm just hoping that you guys understand it, and we will be moving on from there. So the rules for this automata is simple. We will be first defining a third base 2 automata. So the base 2 over here defines the alphabet of our automata. So the alphabet of this automata is going to be 0, 1, base 2 integers, or you could say sigma, which is our alphabet, is equal to z mod 2. Okay. And so we have 0 and 1 as our alphabet, and the rule is like this, or the transition rule is as follows. Transition rule is that we concatenate. Okay, we initialize an empty list. Initialize an empty list or some sort of array or anything. This is step 1. And step 2, we concatenate a letter on two conditions, on the following conditions. So the first one is, if let's say that we're concatenating a letter L. So if L belongs to, let's concatenate, okay, if L belongs to the list, then wherever L is, L should be updated to L++. Okay, or just L+1 mod 2 for this case. Okay, because we're in a base 2 automata, so we don't, like, digits beyond 2 don't exist, right? Similarly, if L does not belong to the list, concatenate L. So for this one, we will start with a base 2 third. And so let's just follow this procedure. We start with an empty list, and there are two possibilities. Either I concatenate a 0 or I concatenate a 1. So in this case, I will have a 0 and a 1. Now in the next case, I can either concatenate 1 again or I can concatenate 0. Oh no, wait, I should write 0 over here. This case as well, 0 or 1. And so in this case, it would be, if I concatenate 1 to 1, so I would get 1, 1. This thing, since they exist, it should increment. So basically, increment mod 2. So I should get 2 mod 2, which is basically 0. This is 0. Now similarly, if I take 0 like this and I put 0 like that, this is 0, 0, the 0 increments, so that becomes 1. 1 mod 2 is still 1, so it stays like that. And so this one is 1. And now here we have 0, 1 and we have 1, 0. And now an interesting question to ask is 0, 1 equal to 1, 0? Or is it at least equivalent? So for this we have to check two things. We have to see what happens when we concatenate 1 and what happens when we concatenate 0. So when we observe what happens in these two cases, since I can only concatenate one of two letters, so I can either concatenate 0 or I can concatenate 1. So this is like, these are all my possibilities, right? So anything I get should be one of these four, right? And so if what do you say, this and this, they act equally or pretty much exactly the same, regardless of what do you say, if they act exactly the same under the same action. So if I do 0 on this and I do 0 on this, and if I get the same one here and the same one here, and similarly on the same note, instead of 0, if I do 1 over here and if I do 1 over here and I get the same output here and here, then I can say that they are acting equivalently. Okay, so let's just extend these arrows a little bit, or let me just erase this. Yeah, so I just erased it, and yeah, so either you have 0 or you have a 1. So in this case you would have 0, 0, 1, 0. So 0, 0 you say increments, so you get 1, 1. It's important to note that the original position increments. So 0 was initially over here, and this is our newer one. So the newer one is basically going to disappear, and the original, the older one, is going to be the one that increments. Okay, just keep that in mind. And we know 1, 1 gives me 0. Similarly, when I start with 0, 1, and then I increment and then I concatenate a 1, so I get 0, 1, 1. And then the one in the original position is going to increment, so I get 0, 2 mod 2, which is 0, 0, and we know this is 1. Okay, so I will just erase it and I'll write it neatly. Okay, or no, I'll just write it over here. So 0, 1, if I put a 0 and if I put a 1, then this gives me 0 and this gives me 1. Okay, similarly, now on this note, I'm going to just erase and I'm going to come back. Yeah, so now we consider 1, 0. So we get 1, 0, 0 over here. The 0, 0 increments original position, remember? So we get 1, 1, and this gives me 0. Yeah. Similarly, over here we have 1, 0, 1 that increments to 1. What do you say? 2 mod 2, 1, which becomes 1, 0, 0, and that goes to 1. Okay, and so basically now I have 1, 0, and if I put 0, I get the exact same thing, and if I put 1, I get the exact same thing. So they are equivalent. Okay, so that is my proof for showing that 1, 0 and 0, 1 are equivalent. And now you'll notice that what do you say, this is equivalent to another element in this graph. So I said 0, 1 is equivalent to 1, 0, because if I put 0 over here, then I get 0. If I put 1 over here, then I get 1, right? And it's the same, it's true for this as well. I claim that it's also equivalent to the empty set, which is true, because if I put 0 over here, I get 0. If I put 1 over here, I get 1. So they are equivalent. These three are equivalent. And so basically this tree, which would have been an infinite tree, because like, if I allow it to be any combination of the digits 1 or 0, is effectively now a closed tree. So I can draw it like this. Let me just refer right to, yeah, okay. So the inner circle is all 1, 1, 1, and the outer circle is all 0, 0, 0. There's a symmetry, so you can just switch the outer circles for the inner circles. The only thing is this arrow directions are going to change. And so this is the state diagram or transition diagram, state diagram of a base 2 third automata. Okay, and so because I'm not going to focus on the application side of this, today's thing is just purely to explain what a third automata is. So that is a base 2 third automata. Now I'm going to go ahead and I'm going to explain a base 3 third automata, which is going to be much more complicated. Right. So I would also like to write down some algebraic equations. Algebraic equations that describe our third automata base 2. Okay, so the equations are the following. Let S naught or let T naught be the transition that concatenates a 0. Let T1 be the transition that concatenates 1. Okay, and then I have the following. So T1 cube is equal to the identity, or basically like the idea is that if I start like this, and I'm not going to put what's inside because what I care about is the relations between them, right? So I have a cycle of arrows going in the clockwise direction, and I have another cycle on the opposite side going anti-clockwise. So if I put T0 over here, T0 over here, T0 over here, and if I put T1 over here, if I put T1 over here, and I put T1 over here, it is the same as the previous example. Only in the previous example, if I had a state like this, instead of T0, I was representing with just a 0. Or instead of T1, I was just representing it with just a 1. So now, yeah, we have these arrows directing us from one vertex or one state to another. And I want to notice that if you start at this point and you do T0 3 times, it is obvious that T0 cube is equal to the identity element, or basically the doing nothing, basically as if it's as good as you never moved. Similarly, T1 cube is equal to identity, and E over here is not the number. It is just notation for identity element. Okay, just to be clear. And similarly, S0 S1 is also not S0 S1. T0 T1 is also equal to identity, which is equal to T1 T0. That's what we meant by this is equivalent to a statement saying that 1 0 is equal to 0, 1 is equal to an empty list. Okay. So this is a third in base 2. And similarly, initially we aim to put these relations out there. Maybe they'll be useful when we're implementing it. But right now, it's more useful to think of it as an automata. Okay, so let me just clear everything. So now we consider a third in base 3 automata. So in base 3, now my alphabet sigma is defined by the letters 0, 1, 2. And by third, we mean that we have the same concatenation rule or transition rule, concatenation / transition rule. So we're using the same rule as before, and it's an automata. And yes, what I also want to just put as a side note, THN or a general end base third seems to have a group structure, which is just something I'm putting out there so that it just says, in the record. So I'm not going to elaborate this right now because that would be a little bit too long to prove that this is a group. So I will just talk about how to do it. Why is it a group structure? Why group structure? So instead of taking it as a group and taking our actions as trying to prove it using T0 and T1 and T2, we instead try to show that the state diagram is equivalent to, it's a Cayley graph of some group. And so it is not clear how to decide. We can show that it is a group because the Cayley graph of a group has certain properties that allow it to be a group. However, it's not clear to me how to prove for a general TH and which group do we get. So for TH2, for smaller examples, I'm sure I can work it out if I need to. To me, it wasn't immediately relevant, and I just decided to treat it as an automata instead. But it would be an interesting question to just solve for a general THN and see what group structure is given in general. It's probably one family, but it needs to be proven still because the structure itself is new. So yeah, hopefully it's a simple group. Anyways, now regardless of why we want a group structure, we're going to forget that we even talked about groups at all. And now we're going to start worrying about a third base 3. Third base 3 automata. So my alphabet sigma is equal to 0, 1, 2. And I have the same rule. And so let's start constructing it, okay? And so I'm just going to go ahead and draw it because I've worked it out already. And I want you to sit and notice what you can. So 0, 1, 2, our identity element as before. You can work it out to prove that 0, 1, 2 is indeed the identity element. And similarly, if I put a 0 over here, then I get 0. If I put a 1 over here, then I get 1. If I put a 2 over here, then I get 2. And then in between this, we have this, where this takes me from, is that right? No, that's not right. It's the other way around. So if I 2 takes me to 0, if I put 0 it takes me to 1, if I put 1 it takes me to 2. And we have, oh dear, I've drawn it wrong. Okay, so 0, 2 over here, which I've shown is later I've shown is equivalent to 0, 2 is equivalent to 2, 0. For the same reason, the proof is the same. Yeah, 0, 2 is equal to 2, 0. And what else? Yeah, so for this, oh no, I can't take it from here to here. Let me just undo that. I can go from here like this. So this takes 2. And then 0, 1. This takes me like this. And then, yeah, this takes me with 0. This takes me with 0. This takes me with 1. This takes me with 1. This takes me with 2. And I get 1, 2. And I have more links that connect from here to here. Is it that right? So 1, 2 goes to 0, 1 and comes from 2, 0. Okay. So it's this way. This is with the 0. This is with a 2. And this is with a 1. And there's one final layer. That is 2, 1 goes to 0 like this. 1, 0 goes to 2. 1, 0 goes to 2 with a 0. And 2, 0 goes to a 1. I forgot where 1 was midway. With the 2, I think. Yeah. And all of these also go to the identity element, here with 2, here with 0, and here with 1. So already you can see that it's kind of a nightmare. And yeah, if you draw it spaced out, then it looks a lot more appealing. And the relations that define this third automata is, instead of T, let's stick with S, because that's what I have written here and it confuses me if I write T. But S naught is the, so S naught will concatenate 0. S1 will concatenate 1. S2 will concatenate 2. And so S naught to the power of 7 is equal to S1 to the power of 7 is equal to S2 to the power of 7, which is equal to S naught, S1, S2, which is equal to the identity element. We also have S naught, S1, the whole square, S naught is equal to S1, S2, the whole square, S1, which is also equal to S2, S naught, the whole square, S2, which is again equal to the identity element. So these relations, these are sufficient relations. Sufficient relations to build the diagram, you could say, or the graph. Okay, so the idea is that basically if I didn't know what anything was and all I had is these relations and these elements, the idea is I should in some sense at least have some full guidance, or at least I should know all of these edges sufficiently well enough to reconstruct it. And so, an interesting fun fact, this is actually, this can be modeled as a real life prism that looks like this. So I can, at each of these vertices, I can put one list element, and I can pretend that these edges connecting them is like is the transition between them. And so this is actually called a augmented triangular prism. And so, yeah, we can 3D print this and we can start labeling edges if we like. Now for 4 digits, I will only give the relations that define them, because drawing them is much worse. In fact, I can only reliably draw an incomplete part. That is without considering what overlaps and what doesn't. So, right, so the following relations are here. S0 15 is equal to S1 15 is equal to S2 15 is equal to S3 15 is equal to the identity element. S0 S1 the whole to the power of 5 is equal to S1 S2 the whole power of 5 is equal to S2 S3 whole power 5, which is equal to S3 S0 whole power 5. So this relation you can say with Si the whole power of 15 is equal to E for I belonging to the alphabet. This is Si mod n and Si plus 1 mod n. Oh no, right, okay, there we go. The whole to the power of 5 is equal to the identity. For the same reason, n over here is just the base over here that we were considering for the third of base n. Similarly, S0 S2 is equal to S3 is equal to S1 S2 is equal to S3 is equal to S2 S0 is equal to the power of 3. I keep saying is equal to S3 to the power of to the power of 3 S3 S1 to the power of 3, and is all equal to E. In this case, what I considered was Si mod n and Si plus 1. No, I plus 2 this time. I plus 2 mod n. And this turned out to be 3. So something I want to point out that is interesting to know, or that would be information of interest, is that if I had Si mod n and if I had Si plus k mod n, so I should get an exponent that is a function of k and n. And for a given third, for thn, what is a k of n? So this is some information that would be interesting to us. And yes, there are more relations that in this case we consider 2 at a time, right? We took 2 of these actions at a time. We can even consider Si, Sj, Sk for whatever relation is between them. Over here, if we had I and j, then we had the relation that I minus j is equal to k or something, in some sense, right? That the difference between them is separated by k. So we can have some sort of relation between I, j, k, and we can try to set our own, over here in this case, bkn or something, and try to figure out what the general expression for it is. So this is what is known about thirds. Let's talk about how to implement this. So to implement this, we will be using a stack data structure. Or sort of, we'll just modify it. There won't be a pop function because we're not removing anything at any time. The push function will not simply add it. We have to check. It has to do two things, okay? It will push, or we can like calculate. Instead, the push function will concatenate. How do I define this well enough? Okay, so the push function has to do two things. If I'm pushing, say, a letter L, let me write that better. Push L. So let me just cut this so it doesn't look like X is part of it. Anyways, so push L, check if L belongs to the stack. If L belongs to stack, then update L in stack to L++. Else concat L to stack. Okay. And what else? Yeah, the updating thing is defined as follows. Update. So for a given n, so say consider a third of base n. So for that, the update is going to be as follows. We want to take L and we want to take it to L+1, the whole mod n. Okay, this is our updating, and I think with that it's clear how to generate it for a general n. Visualization will be another thing of its own, because what this will do is like this, I can view what happens to my stack at any given time. As it updates, I can just view what happens to it, but unless I can actually visualize what it looks like as a state diagram, then we can't move on to the next step. So to start with, we need to at least know how to implement it as such, as a stack. And then we're going to worry about this part. So until then, this much is the idea. And lastly, let me talk about how we're going to apply this to genome sequencing. So I'm going to take a third automata.
Okay.
I'm going to treat it equivalent to a Markov chain. And so what I'm going to do is I'm going to consider this as a Markov chain, and for every edge or transition, I'm going to try to assign some sort of probability of L to each of these edges. And what I'm going to do is once I've assigned the probability, I'm going to find its stochastic graph. Stochastic graph, I say, matrix, which is essentially the adjacency matrix. Adjacency matrix of a Markov chain. And so I'm going to take that and I'm going to find the eigenvector of this matrix, which is equivalent to the equilibrium distribution over all the given states. And so this is what I'm interested in. And what we're going to do is we're going to take our genome sequence I'm going to feed it into here, and we hope to get an equilibrium distribution that tells us something about what's next. So that's enough for today.